In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 3, Yield Criteria, Part 2. Now we have been talking about the yield criteria and the yield function and what are the conditions that should be satisfied for a material to yield. Now here we are trying to show you some geometrical representation of stress and yield criteria. As you can see in this figure, we have three coordinate axes, sigma 1, sigma 2, and sigma 3. And this is a general state of stress. OP has three components on the three stress coordinate axes. So that's P1 on sigma 1, P2 on sigma 2, and P3 on sigma 3. So the state of stress at point P is P1, P2, P3, okay, like sigma 1, sigma 2, sigma 3. And that's the stress vector. Here we have this line of hydrostatic state of stress, this blue line, which makes equal angles to all three stress axes. So it has the same components on sigma 1, sigma 2, sigma 3, and that's why we call it hydrostatic state of stress, because all its components in all directions are the same, right? So that's the blue line showing the hydrostatic component of stress in general. If we can increase the hydrostatic pressure along this line or decrease it along this line. So any state of stress that we have, we could have a component on this line showing the magnitude of the state of stress. Now this is a general state of stress. Okay, I have drawn a perpendicular to that point, so O' is the component of this state of stress. That is the magnitude of the component of this state of stress along the hydrostatic stress line. Okay, so if we had another one like that, then we would have different values. So here for this state of stress, O'P is the deviatory component of stress, and O' is the hydrostatic component of stress. Remember, we drawn these values before mathematically. Now we want to show them geometrically. Okay, so O' is root 3 P, because P is P bar, in fact, is the component of stress at point O'. That's P bar, P bar, and P bar. Along all three axes of stress, P bar is the same, because this is makes equal angles at this stress axis. So O' is root 3 P. Okay, and let's have a look at this again and see what are different of states of stress. For instance, P1 is one state of stress, and for this state of stress, the deviatoric stress is like that, the component of hydrostatic is like that. Now if we change the state of stress to P2, then we will have different components of deviatoric and hydrostatic stresses. Also P3, we will have a different one. So that's the deviatoric, that's the hydrostatic components. And for all states of stress, we could have similar things. Now, if we increase this P1, P2, or P3, any of them, if we increase them, the material will yield eventually. Yeah. So we want to show graphically how that happens. We know from the previous slides that function f j2 equal to 0 gives us the yield point. But graphically, how do we draw that? So that's the function that we had previously, f j2 equal to 0, and j2 we obtained from previous results is equal to this function. Here we have tried to show how the material yields graphically. You see, this is OP, that's the stress, state of stress that I showed you in previous slides. And I said that if OP is increased such that it reaches a value which is high enough, then the material yields. Supposing that is the value that the material yields, OP there. And if that's where the material yields, then if we have a perpendicular to this line of hydrostatic, that will be the deviatory component of stress, and this OO prime is the hydrostatic component of stress. And obviously we can have different of states of stresses for yielding. I mean, it's not a unique value. It could be, for instance, if I draw a line there for POP, okay, a material yields again. So we could have, because as you can see, we could have different combinations of sigma 1, sigma 2, sigma 3 to get this J2. J2 is constant, okay? J2 is constant. But we could have different values of sigma 1, sigma 2, sigma 3 put in there and get the same J2. Therefore, it means that different values of sigma 1, sigma 2, sigma 3 means different vectors OP, because OP has components P1, P2, P3, or sigma 1, sigma 2, sigma 3. So we could find different points on this graph, and all these points represent the yield points. So if we connect these points together, we get the yield locus, okay? That's the yield locus. And clearly we could have other points in here as well. So if we draw this like that, we get a yield surface. So why the yield surface is like that? Why is it like a cylinder? It's like a cylinder. Why is it like that? It's because in our yield criteria we said that the hydrostatic state of stress does not have any effect on the yield point, okay, on the yield value, on the yield function. So this representation, graphical representation, shows exactly that. It means that if we move down here, for instance, okay, and if we have another vector like that, opening P equal to that, there, and if we connect it to there, then we will have the yield. We will be on the yield surface and the material yields, okay. So therefore, it's shown here that the hydrostatic component does not have any effect on the yield function, okay. So if we have a vector like this, the only component that has influenced the yield criteria is the deviatory component of stress. That's what's shown in here. In fact, J2, we showed that only consists of these deviatory components of stress, and therefore the yield surface, as you can see, is a straight line, and this plane, deviatory plane, remains the same throughout here, and it means that whatever the magnitude of the hydrostatic stress is, does not affect the yield. Only thing that affects the yield is this component. For instance, if you have OP somewhere like that, then we or somewhere like that, OP somewhere like that, we will have the same component of hydrostatic stress. But because it doesn't have the same component of deviatory stress, it will not yield. Okay, and this is infinite. For instance, if you have something like that, some curve like that, some component of stress like that, then because the deviatory stress is small, it will not yield. As you can see, it has a very large hydrostatic stress component, but it doesn't have any effect on the yielding. Okay, that is this theory of yielding so far. Now in here, obviously, as you can see, this curve or this locus is around the hydrostatic stress, and this is the center line of this shape. Okay, so this is the center line, and here if we have this deviatory plane, and we could have a similar plane at O. So if we take a projection of this deviatory plane, okay, this green one, the deviatory plane, a projection along this line, and go from O' to O, take a projection here, then we get a plane which is called the deviatory plane or pi plane, which is this one. We will have a plane somewhere here which is perpendicular to this line, okay, because this plane is perpendicular to this line, so all the planes, similar planes, will be perpendicular to this line. So if we take this plane at the origin, then we will have a plane like that. Now why like that? This is a general deviatory plane, because I have drawn like this and that. These are convex and concave curves. We don't know yet that whether it's all convex or all concave, or it's convex and concave. Later on, I will prove that the yield surface must be a convex surface. But for the time being, we take this general view that the yield surface or locus is something like that. Okay? And here we have P1, P2, P3, because in here we had this P1, P2, P3. So we have taken the view from the top, and if we look at it along this hydrostatic line, we will see a plane here, and we will see the views, the top views of P1, P2, P3, which will be like that, all of them in a plane. We call this a deviatory plane. Now we want to see how the stress components change on this deviatory plane. Now what I'm going to do is that I will draw the components of a stress along P1, P2, P3 like this. For instance, P1, because that's O, and that's the positive direction, so this is the negative direction. That's the positive direction, this is negative direction, and so on. So if the stress sigma 1, the magnitude of a stress sigma 1 is A, because it's in the negative direction, we get minus A, so that's the component of a stress for sigma 1. And supposing that the component of stress for sigma 2, this is parallel to that, it means that it is sigma 2 component is B, and supposing the component of sigma 3 is C, plus C because it's in the positive direction, plus B because it's in the positive direction, and as you can see, C reaches the surface. Okay, it means that the material yields. I have chosen the values so that when we add up these stresses, we reach the yield surface. if we go back and there look at this, is something like this OP. This OP has components on P1, P2, and P3, and it has reached the yield surface. So I have shown it here on a plane, on a deviatoric plane. In the previous page, it was three-dimensional view. This is the plane view, okay? Looking at it from the top along the hydrostatic stress line. Right, so that's how we get to the yield point. Now, if you remember, we had three conditions for a material to yield. One was that the hydrostatic stress doesn't have any effect, which because we have drawn this surface perpendicular to the hydrostatic stress, therefore it has no effect. The other condition was that the material properties do not depend on the directions. That means the material is isotropic. In fact, we neglected the anisotropic effect of the material. It means that if we measure the yield strength in one direction and then in another direction, we get the same values. So the yield quantity does not depend on the direction. And the third condition was the Bashinger effect. It means that if we load the material in one direction and then if we load it in the opposite direction, so in the positive direction, in the negative direction, again, in fact, it means that the unloading and loading of the material do not affect the yield point. In actual fact, they do, but we assumed that they don't. So if we want to incorporate these conditions, we should use the J2 criteria for the yield function, and here we are going to show you all three conditions are satisfied geometrically. So I'm going to change the directions and see the signs and directions. You see, the Bashinger effect had to do with the sign of the loading, not the direction. The sign of the loading. And the isotropy had to do with the direction of the loading. So I'm going to change the direction and sign of the loading here and see whether still yielding occurs or not. How I'm going to do that? Like this. Here we are going to apply the loads again, but in different directions. As you can see, in the positive direction, P2 magnitude A, in the negative direction, P1 magnitude minus B, and in the negative direction, P3 C. So as you can see, again, we reach this yield surface while we have changed the signs of the loading, okay, and also the directions we have changed, because here B was in the direction of P2, here B is in the direction of P1. Similarly, we could have we can also change the directions and the signs in other directions like this. For instance, you see that A again is applied at the direction of P1, but here it was minus direction, here is positive direction. Now minus B is applied in the P3 direction, opposite direction, and C also in the positive direction reaches the surface. So you can see three kinds of loading, and with different signs and different directions, and we get the same yield point, okay, on the yield locus. And so it is shown graphically what we have proven before what we have assumed before in the mathematical derivation of the yield function.